Okay, let's dive right into this. Welcome to the Explainer. Today, we are talking about a technology that is just fundamentally changing how our backend systems talk to each other. We are looking at gRPC. So, let's set up our animated journey into the world of microservices where, as we all know, speed and efficiency are absolutely everything.
Think about your current setup for just a second. If you're building distributed systems today, you're probably relying heavily on REST APIs and JSON to pass messages back and forth, right? I mean, it's the industry standard. It's human readable, it's relatively easy to debug, and, well, it works. But what if I told you that all that human readable text is actually creating this massive invisible bottleneck? What if your microservices could talk up to 10 times faster using just a fraction of the bandwidth and CPU?
Enter gRPC. This is our hero for today's explainer. Originally developed by Google, gRPC is a high-performance, open-source remote procedure call framework. Now, remote procedure call, or RPC, simply means a program can execute a procedure in another address space, like, say, on a completely different server, as if it were just a normal local function call. But gRPC supercharges this really old concept by combining two modern powerhouses, HTTP/2 for transporting the data, and protocol buffers for serializing or packing that data. It literally replaces bulky text payloads with lightning-fast binary communication.
Part 1. Meet gRPC, the basics. To really understand why this is such a massive leap forward, we kind of need to visualize what's actually happening under the hood. So I want you to imagine your data payloads as physical objects. In the traditional REST and JSON world, your data is like a giant, fluffy marshmallow. It's bulky, it takes up a ton of space, and it's just slow to move around. Every single time you send a message, you're sending all those field names, all those curly brackets, all that white space over the network. gRPC changes this entirely. Instead of a marshmallow, picture your data being handed to a tiny, lightning-fast delivery bot. This bot compresses your data into a hyper-dense, squished binary laser beam. There's zero wasted space, no field names sent over the wire, just the raw compressed values.
And this delivery bot doesn't drive on some old, bumpy dirt road. It zips across a massive multi-lane highway. This highway is HTTP/2. You see, older systems using HTTP/1.1 often suffer from something called head-of-line blocking. That's basically a massive traffic jam where requests literally have to wait in line for single connection. But HTTP/2 features something called multiplexing. This means multiple requests and responses can travel concurrently over a single long-lived TCP connection without blocking each other at all. Our little data bots can just weave in and out of traffic instantly.
And this brilliantly illustrates the core difference we're talking about. On one side, we have heavy REST and JSON. It's synchronous, text-based, and relies on those bulky payloads that just chew up bandwidth and CPU cycles simply to parse the text. On the flip side, we have lightweight gRPC. It uses multiplex streams, strongly typed contracts, and that hyper-dense binary serialization we talked about. The efficiency gains here are absolutely staggering when you start scaling this up to thousands of requests per second.
Moving on to Part 2, the magic protocol buffers and a tiny .proto example.
So how does gRPC actually squish that data down so perfectly? Well, the secret sauce is protocol buffers, or protobufs for short. Think of them as an unbreakable cartoon contract, or like a menu between your client and server. Here's a tiny real-world example straight from the protobuf documentation. This is just a 5-line .proto file defining a search request. Notice the structure here. We have a string named query, an integer for page number, and another for results per page. But look really closely at the end of those lines. =1, =2, =3. These aren't the actual values. These are uniquely numbered tags. Because both the client and the server have this exact same file, they don't actually need to send the long word page number across the network. They literally just send the number 2 and the value. And that is why the binary packing is so unbelievably tiny.
And honestly, protocol buffers give you some serious superpowers. First off, they're completely language neutral. You define your service once in this .proto file, and you're good. Second, the fields are strongly typed, so no more guessing if a value is a string or an integer. Third, and this is a massive time saver, the protocol buffer compiler automatically generates the working data access and networking code for you in almost any programming language, whether that's Go, Java, Python, C++, you name it. And finally, because of those numbered tags we just looked at, you get built-in backward and forward compatibility. Meaning you can add or remove fields without breaking your existing services in production. How cool is that?
All right, Part 3.
client and server action.
To see how these generated pieces actually build into a working system on our cartoon assembly line, let's consider what happens when you generate your code. gRPC creates something called a stub on the client side. You can think of this stub as a magical local proxy. Step 1. Your client application just calls a method on this local stub, exactly as if it were a normal local function. Step 2. The stub does the heavy lifting of marshalling. That's our cartoon delivery bot packing the data into that super dense binary format. Step 3. The gRPC infrastructure sends this packed message over that HTTP/2 multi-lane highway. And finally, Step 4. The server receives it, unmarshals or unpacks the data, and executes the actual service logic. The reply then traces these exact same steps in reverse. It completely abstracts all the complex networking away from the developer. It's basically magic.
Which brings us to part 4, streaming and deadlines.
Now, what's really interesting here is that because we're utilizing the power of HTTP/2, gRPC goes far beyond simple request and response. It actually gives you native support for continuous streams of data across 4 distinct streaming patterns. First up is unitary. That's your classic single request, single response. Then you have server streaming, where the client sends one request and gets a continuous stream of responses back. That's great for live data feeds. Client streaming is the exact opposite. The client sends a stream of messages, and the server responds just once. Perfect for uploading large files. But the absolute crown jewel is bidirectional streaming. Both sides send a sequence of messages using a read-write stream completely independently. Imagine a high-speed ping-pong match where both players can serve and return balls at the exact same time without ever waiting for the other. It is incredibly powerful for real-time chat, multiplayer gaming, or live dashboards.
But, with all this continuous connection power comes a very real danger: resource exhaustion. Grainy Sheeran, a site reliability engineer at Google, puts it absolutely perfectly. TLDR, always set a deadline. A deadline is essentially a ticking time bomb set by the client. It tells the server, hey, I am only willing to wait 100 milliseconds for this response. If the server takes too long, the client just drops the connection with a deadline_exceeded error. If you don't set these, hanging requests will just pile up and your servers will eventually run out of memory and crash. Deadlines are what keep your system healthy and clean.
Part 5. Why choose gRPC?
So the crucial point is, why should you go through the effort of learning protocol buffers and rewriting your APIs to use gRPC? Well, let's ground our cartoon bots and highways in some hard data from the research. The advantages are broken down into 3 massive pillars. First, latency and throughput. Because protobuf is literally so dense, it uses up to 10 times less bandwidth than JSON. Second, resource utilization. Parsing binary data is vastly easier for a computer than parsing text, meaning gRPC can be deserialized using 50 to 80% less CPU usage. And let's be real, that translates directly to lower cloud hosting bills. And third, support for real-time applications, which are natively handled by those bidirectional streaming patterns we were just talking about.
As we wrap up this explainer, I want to leave you with a question to ponder about your own architecture. Look at your server costs. Look at your API latency. Are you ready to upgrade your microservices from walking to teleporting? Seriously, how much bandwidth, memory, and CPU are your current systems wasting simply by forcing your computers to read text instead of binary? gRPC definitely has a bit of a learning curve, sure, but the performance ceiling it unlocks is truly next generation. Thanks for joining me on this explainer, and I hope this sparks some great ideas for your next big project.